Hi, everyone, and welcome to Data Engineers Lunch number 33. Been through quite a few of these now, almost a little over half a year's worth of Data Engineers Lunches now. Today, we are going to have a junior software engineer here at Anant. Oh, I didn't change the name. That is my bad. That is not me. It's actually Nikita. Pearson is going to be leading us today. He's going over using Spark, Cassandra, and Elasticsearch for data processing. Sorry about that, Nikita. The organizers for this event are Raul, Arpin, and myself. And we are always looking for more speakers and sponsors. So if there's a particular topic you are an expert in or something you want to learn and then go ahead and share with the rest of us, feel free to reach out to mainly Arpin or myself now are the ones running things, as Raul's pretty busy. So definitely don't hesitate to reach out to us if there is something you'd like to share or speak on here. In addition to that, if you know any organizations that would like to sponsor, once we're, I don't know when we might go back to having in-person meetups, but sponsors could get something like food or drinks for everyone. So yeah, if that's something you or someone you know would be interested in, definitely reach out to Arpin and myself as well. We are part of a larger community. Data Community DC does believe in a diverse and inclusive culture. So regardless of race, gender, sexual orientation, religion, all protected classes are welcomed here, and we expect respect to be given to everyone equally. Some of the other organizations associated with Data Community DC are listed here, and you can find out more at their blog, datacommunitydc.org/blog, and they also have other events as well, which that link is listed here as well. So what we cover here at Data Engineers Lunch, we cover everything related to data engineering. You can see sources, ETL, dashboards, and machine learning. We kind of cover everything. So again, going back to if it's something, if you'd be interested in speaking or presenting at one of these, you're really not limited to topics. As long as it's about data engineering, we'd love to hear what you have to share. This is a point in the introduction where we like to encourage any new members to go ahead and unmute themselves and introduce themselves to the rest of the group. I do see a fair amount of new faces here, so if anyone's feeling confident and would like to unmute themselves and say hi and what they do with data engineering, feel free to do so now. Well, if you guys are shy, I won't call anyone out specifically. And we can go ahead and move past. So group rules, if you have a question, ask it, be polite and courteous to others, and share what you know. This is meant to be a discussion. Nikita may have his own way he likes to handle questions, so he'll clarify that when he takes over. Sometimes speakers prefer questions be dropped in the chat, or sometimes people can unmute themselves and just ask. And other times, speakers would prefer to dedicate a specific time in their presentation to answer questions. So here at Anant, we deal with big data and real-time data platforms, specifically Cassandra, Apache Spark, and Kafka. And DataStax is a partner with us. So I'm sure you guys are familiar with DSE, the enterprise version of Cassandra, as well as George Washington University. I know pre-COVID times, they allowed us to host our meetups there at their facilities. Hopefully we'll be able to get back to that at some point in the near future. And to shout out to some of our program sponsors, you can see those listed here. And if you or someone you know wants to sponsor us, they could also be added to this list and get a little shout out every week on Mondays. And some of the organizational sponsors to Data Community DC are listed here as well. This is a point in time where if anyone has jobs, meetups, hackathons, conferences, or classes coming up, feel free to unmute yourself and share whatever event you have coming up. Okay, doesn't seem like anyone has something to share here. Bit of our own announcement. Anant is hiring for full-time or part-time data platform operators, engineers, and architects. You can find out more at careers.anant.us. So if you or someone you know is an expert in these fields or has a role such as these, definitely come apply to work with us. And some of our upcoming events, you can find listed at anant.us/events. We are going to be doing, specific to Data Engineers Lunch, doing an introduction to Snowflake. We'll be covering dbeaver, as well as Alessandra, Kafka, and Spark. There is the sister lunch to this, Cassandra lunch, that occurs every Wednesday at noon. And all these events are listed at anant.us/events. So definitely don't hesitate to go there and check out what we have going on this month. And that is all I have for the introduction. So if Nikita, I will pass it off to you.
All right, thanks for the intro, Josh. So I'm going to share my screen here in a second. I think it works, right?
Yeah, I can see it.
Okay. So, as Josh had mentioned earlier, if you have any questions, then you can either unmute yourself and ask the question, or you can just type something in the chat, and hopefully I or someone else in the chat will be able to answer your question. So today I'm going to talk a little bit about using Spark, Cassandra, and Elasticsearch for data processing. Let's see. All right. All right, let's try that again. All right. I'm presenting this. Oh, okay. So first, I'm going to talk briefly about each of these technologies separately, being Spark, Cassandra, and Elasticsearch. Then I'm going to go into some details about the demo project that I have prepared for this. We'll link the demo project, or I'm not sure if it's public at the moment, but if not, then it will be shortly after this talk. And then we'll also have it linked in the blog that will be about this topic in a few days. And then after going through what the demo project does, we're going to look at the repository for the project, run the demo project, and then in the near future, you'll be able to take the project and do all this yourself at home. It's pretty cool. So the first technology we're going to talk about is Cassandra. Apache Cassandra is an open source distributed NoSQL database designed to handle large volumes of data across multiple different servers. And with Cassandra being distributed, one of the cool things about it is that Cassandra clusters can be upgraded by either improving hardware on current nodes, which is called vertical scalability, or adding more nodes, which is horizontal scalability. And so horizontal scalability is part of why Cassandra is so powerful. So typically with a relational database, if you wanted to improve the performance of the database, you'd have to improve the hardware that the machine itself is running on, or that the database itself is running on. But with something like Cassandra and other distributed databases, you can just add more nodes that can be made of like relatively cheaper computers, and you can still get significantly increased performance of your database overall. And then one thing I want to note, which I'll also mention later, is that the demo runs the DSC or DataStax Enterprise version of Cassandra, not open source Cassandra. And Spark is also run together with Cassandra in DSC with analytics mode enabled, but it's very possible to do everything that the demo is going to be doing today with open source technologies, or with the open source version of Cassandra. Right. So Apache Spark is an open source unified analytics engine for large scale data processing. It provides an interface for programming entire clusters with implicit data parallelism and fault tolerance. As I'd mentioned a minute before, in this demo, Spark is being run from DSC with analytics turned on, but Spark can also be run separately. Doesn't even have to be on the same machine. You just need to set up a master node and at least one worker node to accept and perform the jobs that we're going to be giving it. Now we're going to briefly talk about data structure in Spark SQL called data frames, or rather sort of the evolution of this data structure. So the first version of this data structure, I guess, was called RDDs, or Resilient Distributed Datasets, which have been available since Spark 1.0. Primary user-facing API in Spark since the very beginning. It is an immutable distributed collection of elements of your data partitioned across nodes in your cluster. That's where the distributed part comes from. And then, starting with Spark 1.3, they released something called data frames and data frame API, which data frames are also an immutable distributed collection of data. But unlike RDDs, data is organized into columns with names. So think of like a data frame as kind of like a table from a relational database. And data frames allow for a developer to impose a structure onto a distributed collection of data. Also, there are a bunch of APIs that let you do a bunch of cool and useful data manipulation related things with data frames as opposed to just RDDs. And then even more recently, there's a data structure called data sets since Spark 1.6, which, unlike a data frame, which is a collection of generic untyped objects, data sets are strongly typed. So you can kind of think of data sets as an extension to data frames. A collection of strongly typed JVM objects dictated by a case class you define in Scala or a class in Java. And one benefit of this is that the syntax and analysis errors both come out at compile time as opposed to runtime. So you'll be able to catch a lot more errors with typing and such, not at runtime. Now we'll briefly talk about the last piece of the puzzle, Elasticsearch. Link their website. And Elasticsearch is a distributed open source search and analytics engine built on Apache Lucene and developed in Java. Elasticsearch allows a user to store, search, and analyze large volumes of data quickly and in near real time, returning results in hopefully milliseconds. Talk about a couple basic concepts of data in Elasticsearch. First, I'll mention documents. Documents are the base unit of information that can be indexed in Elasticsearch, typically expressed in JSON format. So you can think of a document kind of like a row in a relational database. So the thing that you're going to be searching for or looking for, and how you're going to be storing your data. An index is a collection of documents which are similar in some way. Documents in the same index are typically logically related. So you can kind of think of an index as like a table in a relational database. And then a thing that Elasticsearch builds for you is something called an inverted index, which is a mapping from content. So in particular, Elasticsearch is used often to where you have a large amount of data, like a very large amount of documents or web pages or blogs or whatever, and you want to have a way to very quickly search through them and return results. So you can find the documents or blogs or whatever that you're storing easily. And so an inverted index is a mapping from content. So in Elasticsearch in particular, you would use, or that would be like individual like keywords to places that content or those keywords are located, which in the case of Elasticsearch, that's documents. And then the demo project itself is primarily it's code written in Scala, and then it will be run on Spark. And to build that code, we use SBT. SBT is an interactive build tool for Scala and Java projects. A large majority of Scala projects are built using SBT, and the demo project in this case is no exception. This demo project uses a plugin called SBT Assembly, which creates something called a fat jar, which is basically where you have one jar file that your classes get built into that contains all the class files from your code and also all of the necessary dependencies. So when you send a fat jar to Spark to run, you don't have to worry about what is like locally installed on your Spark cluster. It should be able to run everything as long as you send it a fat jar. Put a little link to SBT assembly, and more info about SBT can be found on their website. Sorry about that. All right, so now we're going to talk about the demo project. This is a link to the GitHub repo for the project. The demo project contains 3 Scala class files, each corresponding to a separate Spark job. And the 3 Spark jobs that we're going to be going over are as follows. The first job will read a .csv file into a Spark SQL data frame and save it to Cassandra. The second Spark job will load data from a Cassandra table into a Spark SQL data frame and then save that data into Elasticsearch. And the third Spark job will take data from Elasticsearch, load it in from Elasticsearch into a Spark SQL data frame. And then also part of this demo project is a Docker Compose file, which runs 2 Docker images that are set up to know how to talk to each other locally. And the 2 Docker images that will be run as part of this Docker Compose file are DSC, or DataStax Enterprise version of Cassandra with analytics enabled, which is where we're getting Spark from. And also the second Docker image is Elasticsearch. In this case, happens to be 7.13, which is either the most recent or close to the most recent version. So now we're going to take a look at the repository. So another cool thing about this demo is that it comes with a pretty detailed README file. So even if you only have the link to this repository from this entire talk, then you'll be able to take the README file, follow the instructions in the README file, just as long as you make sure you have requirements downloaded on your machine, and follow all the commands and make sure that everything works as it should. So I have the repository downloaded here, and the first thing I'm going to do is run this Docker Compose command, which is going to run our Docker Compose file. And if we type in docker ps-a, then we can see the 2 containers are running now for 6 seconds. One is DataStax Enterprise, Cassandra, and the other is an Elasticsearch container. We're going to have to give these a couple minutes to boot up. But while they're booting up, I'm going to show the basic data that we're going to be importing today and the structure of the Cassandra table that we're going to be using for the data. So this is the CQL file that we're going to be using in a minute to create the key space and table in Cassandra. You see, we're just creating a basic table called test.users, or the table name is users and the key space is test. And it's just a table with 2 fields. One is just ID and second is username, both text, and primary key is just 2 of these combined. All right, let's see. It's been up for a bit over a minute, so we should be good to start running some more commands. So I'm going to clear the console. Next, we are going to use the following command to set up the test Cassandra table, which is just going to run this CQL file in CQLSH on our DSC container. So we're going to put that in. Now, if we list the two containers that we have again, and we get the name for the DSC container, it's this one right here, then we do Spark Cass ES DSC1 CQLSH. Then we can run CQLSH on the container that that we're running DSC server in, and then we can describe test.users, and we see that we have inserted our Cassandra table into the database correctly. Additionally, if you don't perform this step of manually checking through CQLSH that the table has been, or the key space in the table have been correctly inserted, then you can also just try running the next stage of the project, and well, if things don't work, then this is one of the first things to try and diagnose. Next, we run SBT assembly, which uses the SBT assembly plugin to build our project. And this might take 30 seconds, a minute. And so we have 3 separate class files that contain the code for the project, but we're going to be building it all into one jar file along with all the necessary dependencies. And then when we're performing, or when we're giving instructions to Spark Submit, we are going to be giving the class name that we want to run for each individual job. So the commands that run the 3 individual jobs are mostly the same, aside from this class flag, where we're going to be putting in a different class name for the 3 different Spark jobs that we want to run. All right, it seems like everything's built, no issues. So now we're going to run the first Spark job, which is going to take data in our local file called data.csv, part of this database, in the test data directory. And it's going to take that data, load it into Spark SQL, into a data frame, and then we're going to save it into DSC Cassandra. All right. So another thing is that this may look like it's taking a really long time to run all of this. And with the very small data.csv file we have, it may seem like this won't scale very well. But the actual process of the job being run and loading the CSV file and saving it to Cassandra happens in like milliseconds, like a millisecond probably, or some very, very small amount of time. The time that it takes for every job to start up has something to do with how we're using Spark from DSC Cassandra. So it has to like boot up Spark nodes before every single job that we're running here. So that's mostly what's taking time. But the actual, if you look at the,
not nodes, workers and executors.
sorry, yeah, yeah.
Node is already up.
Yeah. So if you look at the timestamps in these logs, or whatever shows up in the console, if you look at the timestamps between when the job actually starts and when the job ends, it'll be very, very, very small amount of time. And then we see here in the console that we've printed the data, which we've tried to add to Cassandra. So we know that we've at least managed to load the CSV file into Spark SQL. And then I can go back to the command I used previously to open up CQLSH in interactive mode on the Docker container that's running DSE. And then we can run select star from test.users, and we have all of our data, which is pretty cool. Now, just check that both of our containers are still running. Yep. So the second job now is going to take data that we just put into Cassandra and load it from Cassandra into a Spark SQL data frame. And then we're going to save that data to Elasticsearch. I'm going to see what happens.
Also, the most of the Scala code, you can, I mean, all of it, you can kind of copy and paste it into a Spark shell, and it will run a lot faster. It's just when you do a Spark submit, it has to like copy the jar to the Spark node. So if you have 100 nodes, it has to copy the jar to potentially 100 nodes or whatever. Or if it's using a HDFS, it puts it into HDFS, and then from there, it copies it. But yeah, you're right. Like the actual processing, once it's primed up and ready to go, it's like nothing.
Yeah.
I also kind of use the analogy of like, so you're trying to build a doghouse, and Spark is like an army. So do you really need an army to build a doghouse? Probably not. But to like make a castle, yeah, sure.
Hey. All right. So it seems like the project has run. There we can see some portion of the job took half a second. All right. I did not mean to do that. So now, as we have Elasticsearch running in a Docker container locally, we can visit Elasticsearch through our web browser, and we can see that we have put in our data. Right, we have ID username, ID username, ID username. So our very not super interesting data, but it's the data that we wanted to input into Elasticsearch nonetheless. And every row of this data CSV file has just become a separate document. And by using this command on this test index that we put it into, where I just called the test index user test index, and then if we go to underscore search, then it shows us everything in that index. Or rather, I think by default, it's only returning 10 results, where we have a few more than that. That's pretty cool. And then finally, we're going to go through the third job, which the third job then reads from Elasticsearch index that was created in the last job, and we put this data into a Spark SQL data frame. And then afterwards, we will display the data that we got from reading Elasticsearch in the console. And then I will briefly mention something about filtering. And yeah. This again will take another minute. As Rahul had mentioned, all of this code, if you had an interactive Spark shell running, then you could copy paste this code straight into that Spark shell, and it would run it like that, instantly. Hopefully at some point we see our table being displayed. All right, there it is. I think something that I didn't do so if we notice here, our original data was only 13 lines, right? But from this Elasticsearch return, I know that the font is really, really small, but it actually says that we have 26 results in our test index, as opposed to the 13 that we would expect. And if we also look at our terminal output here, we can see that all the data that we loaded in from Elasticsearch, it's showing, well, only top 20 rows, but there would also be 26 then. And so the reason that this is happening is that I believe if we go to the Docker Compose file, we can see that the Docker Compose files stores Elasticsearch's data into a local volume. And so I ran this project to test just a few hours ago to make sure everything was working, but I didn't clear the local volume from the previous test run. And so when I rerun the data, it's reinserted again into Elasticsearch. So we have 2 copies of every piece of data. So that's why we're getting 26 results in Elasticsearch as opposed to 13. But if it's your first time running the project all the way through, then you will only get 13 results. But yeah, we have results from Elasticsearch. So all 3 Spark jobs seem to be doing their job. And another thing that this the README file in this repository talks about a little bit is about filtering data. So, like, do we have to go through, or basically, when you put filter conditions into your thing in Spark that deals with actually pulling data from Cassandra or from Elasticsearch, it will push down most of the conditions that you put in, assuming you create them properly, so that it's not going to query like the entire Cassandra database or the entire Elasticsearch database. It's going to do things properly. So if you're working with larger sets of data where you have, millions of lines, but you're only querying for 100 of them through filtering functions in Spark, then you won't have to hit the entire database, and things should work as you'd expect them to. And then another thing I wanted to mention was that some number of weeks ago, maybe 2 or 3 months ago, another member of the Anant team, Arpan, he had a talk on where he loads data into Spark SQL data frames from a CSV file, and then also loads this data into Cassandra. But in addition to just loading data from a file and then into Cassandra and then into Spark, Arpan's demo project also does some data manipulation. So that's something that is pretty cool to look into, and is part of the reason that you use Spark SQL data frames in the first place, is that you typically want to do some kind of data transformations. So I will link this in the chat, and also I'll make sure to mention it in the blog. Where's the chat? This one right here. And then when you're finally done with the project, you run Docker Compose down, all the containers will be stopped, and you'll be good to go. Oh, aside from the Elasticsearch data still being stored locally on your machine, and you'll have to remove that manually if you want to start with a clean slate on Elasticsearch. All right. And that's about all that I have for today, aside from this little list of resources.
Were you gonna, maybe I missed it because I stepped out, but were you gonna show the code for each of the classes?
I could very briefly show the code. Yeah.
Yeah, I think it'd be useful to show
So
people exactly what's happening.
Yeah, 1 second. So the first class is called load into Cass. Should I make the font bigger? Is the font large enough or should I make it larger?
Make it a little bit larger.
All right.
I think the same as like into Control
Preferences.
Plus.
Oh, I know this method. All right. So the code for a lot of these projects is actually, or for these 3 jobs is actually pretty simple. Part of the reason for this is just how Spark Session works nowadays. There used to be like, basically you'd have to have like separate, like there'd be a CQL session and Spark Session and some other session. But nowadays you just use Spark Session and you can do a bunch of different things, like we'll connect to a bunch of different databases and data sources and things along those lines. And so for the first project where we just load data from a CSV and then save it into Cassandra, we have the name and the directory of our file. We have the Cassandra key space and table name. And then we read in CSV format with the option of header being true. So what that means is that we skip this first line because our CSV file has this header line. So we don't load that in as data. And we're loading it locally. And then once we load this in, we show the data frame with the .show command. And then we can just take the data frame and do .write, .cassandra format, plug in our table name and key space name. And as long as we had configured things properly up here, meaning we had to create a Spark conf object at first and tell it our Cassandra database's location, or like where it's hosted, and then the username and password you need to get into the database. But as long as these things are all properly set up, then you literally just write .write, .cassandra format, and your data saves. And then if you were working with a remote database, then most of your changes would just be right here. And you should be able to save and load from a remote Cassandra database without too many issues. And then for the second file, or the second Spark job, where we load from Cassandra and then save into Elasticsearch, we again create the Spark conf object, but this time we have to give it a few extra things because now we're also working with Elasticsearch. So we give it some info that it needs for Elasticsearch, like es.index.auto.create. What that does is basically, if I'm saving to Elasticsearch and I'm telling it to save to some my index, or to some index called my index, but I haven't actually created the index yet, then it'll automatically create the index for you, which in any kind of actual environment where you're trying to use this for meaningful data storage and searching and usage, then I'm not sure you'd want to have this on, but for the sake of the demo, that's what I used. But I also could have just created the test user index in Elasticsearch first, and then not have to use this option. And again, once we have our Spark conf set up, we just have our Cassandra table and key space name. To read from Cassandra, we just do spark.read.cassandra format. It reads. And then we can, save it to Elasticsearch with, take the name of the data frame and write .save to Elasticsearch. And we give it the index name to save to. And then finally, the third Spark job. Again, we set up a Spark conf object. This time we only tell it things about Elasticsearch because the third Spark job doesn't deal with Cassandra at all. It only loads from Elasticsearch. We give it the name of the index that we're going to be reading from. And then we just tell it to read all of the data from this index and then show it off. And yeah.
I mean, this is as close as you get to select star from insert into in the NoSQL world. which is really cool in relational databases. And actually, you know, in a select star from insert into, like in the middle, you can do SQL transformations on the data. You can do that. I don't think you're doing any transformation in the middle, right? You just load the data frame and then you push it in there.
There's no
But like
transformation.
technically you could do a bunch of manipulations to this data before you send it on its way.
Yeah.
But yeah, I think this is a really powerful demo. I don't think people quite understand, but like this thing can run on one computer or it can run on 1,000 computers and it'll work exactly the same. That's really cool.
Yep. All right. And that's all I have to show for today's data engineers lunch.
Any questions from anybody?
I have a question. So it seems to me like we're reading data from Elasticsearch and we're storing data into Cassandra. Can you tell me what's the benefit of having both? Do we have like duplicate data, and what's the benefit of using Cassandra here?
Could you repeat that question one more
Right,
time?
so the data is stored on Cassandra, right? And in Elasticsearch. Because when we read the data from Elasticsearch, we're reading it from a local Elasticsearch database, right?
Mm-hmm.
So isn't there duplicate data right here? And why are we using Cassandra? What's the benefit of it? Can we just store the data into like Elasticsearch? Is what I'm like. I mean it.
Well, I would imagine that I would imagine that Cassandra is probably better at storing extremely large amounts of data as opposed to Elasticsearch. I can't think of a use case off the top of my head. I think Raul can probably answer that question better, but
yeah, can somebody mute the random people that are not muted?
yeah, there we go.
Okay. Yeah, so good question. I'll give you some background as to why you would want to do this, because like one of the first projects I ever worked on with Spark, Cassandra, and it was actually with Solar. So Solar and Elasticsearch are both very similar engines in that they are powered by the same Lucene search index technology. And the goal for this project that I was working on was to create this like massive search engine with, I don't know, 120 million documents. And so Cassandra was used as the staging area, and meaning from various different engines, like people had Java code, people had Scala code, but they would put the data into Cassandra in a standardized table. And then we would use Spark to take it from Cassandra and put it into Solar. Now, at that time, and still DataStax has its own Solar index. But as always, with an integrated product, you know, it's a few versions behind from the bleeding edge. And so there were some features in the latest version of Solar that we couldn't really get it to work in DataStax. So we stood up a separate Solar cluster, and we used Spark to synchronize from Cassandra into Solar. And that's a common thing in building search indexes. End of story. Like you have to stage the data at some point. Commonly, people will say it's basically, instead of calling it extraction, transformation, and load, it's ingestion, enhancement, and load, or ingestion, load, slash enhancement at the same time. And so when you have data in Cassandra, and let's say you did not have DSE, right, and you wanted to search data from Cassandra in the way that you can do it in Elasticsearch, which is on anything, any text, any string that's in there, you could just search for it. You wouldn't be able to do that in Cassandra without Spark, but even then, it would have to scan all the data and get all the data onto Spark's side, then do a filter, versus if you put it into Elasticsearch, it's like a very quick result. But that's the maturity of an architecture, is that eventually people see that no one tool is going to solve all your problems. You have to really use the best of what's available. So for example, Wikipedia, technically the back end of it is MySQL and PHP, but they have a rendering engine that uses Node.js, for example. And when you go to a Wikipedia page, it actually renders that page and saves it inside an API backed by Cassandra. That's why millions and billions of people can go to Wikipedia and like everything is cool. At the same time, Wikipedia, when you search it, it doesn't use a MySQL search. It doesn't use a Cassandra search. It actually uses Elasticsearch, right? So in that massive platform, they're using MySQL, they're using Cassandra, and they're using Elasticsearch. There may be some points where you want all the data to get synchronized between all these different systems in a very methodical and systematic way, so that like 100% of the data is synchronized. That's when you would use Spark to connect the two. Hopefully that explains why you use different databases.
Yeah, I think I get it. We won't worry about that much about duplicate data as much as other aspects of the architecture, right?
Yeah, disk space is cheap. How much is like a 10 terabyte disk now? Like $100? Like, I don't know. Data storage is super cheap. Even SSD drives are fairly cheap. But that's the beauty of like an index like Elasticsearch, is that you can have massive amounts of data, and the index you can configure it so that it doesn't store all the data, it just indexes it. And that index is going to be way smaller than the data itself. And it can hold a whole index inside memory. And it's like super fast. So yeah. Good question.
Thank you. Thank you.
Hey guys, new to the meetup. My name is Raj. I have another question. I was just wondering, what is the theoretical upper limit to the size of a CSV that you can load into memory on a Spark cluster? So would it just be directly proportional to the number of nodes you have in the cluster? Or is there any, or would you say there is any upper limit to the size of the CSV file that you can load into memory at once?
I can take that, Nikita, if you.
Yeah, I don't know.
Yeah. So I mean, the example that Nikita is using uses file : // right? So meaning it's just coming from a local disk. So technically, if you were in a distributed environment, you would use, if you had 100 Spark nodes, you'd want to use a distributed file system like S3 or HDFS or Google FS. And so in that case, like technically there's no limit. And depending on which library you're using, I think which CSV, you're using the built-in CSV library, Nikita, for loading the data, or did you use the Databricks?
I think built-in.
Yeah. So I think Databricks has a CSV library, but depending on which one, I don't think there's an upper limit, but most people won't. Well, I don't know what most people do. I know what I've seen is when you start to have like really, really massive CSV files, generally people will break it apart and do their own quote unquote partitioning. So like CSV data by date, right? And then every day there's like a big massive CSV file. I don't know at the end of the day, like, what the performance differences would be if you have a broken apart a CSV versus a very massive one. Ultimately, Spark is going to have to scan and break up the scan essentially, and internally it's just kind of doing a map reduce. But yeah, I mean, I've ingested like I don't know, like a 5 GB CSV file, and it did it pretty quickly because that can just happen on one machine. But I've never tried to do like a terabyte size CSV. Technically, it could still do it because it would break apart the work. But that's a good experiment.
Yeah. I was just wondering if the upper limit for the memory is the combined memory of all the nodes, or is it going to be the memory for one node only? Does that make sense?
Oh yeah, no, sure. So
Yeah.
as with I think Gotham put something. So technically, what Gotham you're saying is correct, but the whole point of Spark is that it takes a massive job and it can break it apart. So let's say you have you ingest something into a data frame, right? It technically just represents what is stored on disk. It's not in memory at that point, right? Nothing has happened to the data. It just represents what's in the data. So if you have a data frame that's backed by Cassandra, it's just a representation of it, or it's like a pointer, or if it's Elasticsearch, it's just a pointer. Until you do an actual transformation on the data frame, nothing has happened. So it doesn't have to fit into memory, right? It just has to basically understand where the data is. When you do a transformation, it will then take it, and depending on the underlying technology, it will determine the best strategy or plan to retrieve the data, do transformations, and save it into the other data frame. Now, if you're going to store a data frame that's 100% in memory, then yes, you do need to have the memory available. But you're able to basically back that data frame with, let's say, Parquet. Parquet is like a file format, right? So commonly, if people are going to do very, very massive transformations, they will stage it in Parquet because it's cheap. It's just disk, or they'll store it in Avro or Orc. There's like several different file formats that you can back a data frame with inside Spark. But the whole data set does not need to fit into the data frame memory. It's just the transformations. And even the big transformations, if you were to do the transformation on the full data set, it should plan the work and do it in the constraints that it has, right? So if you only have so much memory, it will do a certain set of the data, and it does it in stages. You can see it in the Spark UI. If you have more memory, it'll do it in few stages, versus if you have less memory, it'll do it in multiple stages. But eventually, in each stage, it can break up the work. And I've seen this with like massive amounts of data, terabytes of data, on big clusters and on small clusters, and it works fine. You don't have to have a terabyte of memory, basically. It works by breaking apart the work.
Yeah, makes sense. Thank you. Yeah, it's a good experiment to try out, I guess.
Yep. I mean, in terms of processing large amounts of data, there's basically, well, there's lots of different technologies out there today, but for a batch processing task, basically Spark is kind of the king in this world right now. But the up and coming is the streaming methods of like Flink or via Kafka streams, but neither of those give you the benefit of being able to do cross-record processing at such large scale. So in Flink or in Kafka streams, generally you're transforming that one record, and you're putting it somewhere else, and the next stage picks it up, and you have to build out that topology. I think Flink maybe can do it for you, but in Spark, you can do both streaming and very, very large data set operations, as long as you have the number of machines. Basically, you got to have the hardware, but it can do it without croaking, right? It's not dependent on a particular record or time window. It's just taking the thing and breaking it apart and doing it. Good question. Yeah.
Yep. Thank you. Thanks.
We are almost out of time.
Yep.
All right, folks. If there aren't any other questions, I think we can call it a day.
Yep.
Hey, Nikita, thanks so much. And Josh, thanks for starting us off. And Elena for being director today. You guys have a wonderful rest of the week. We are here every Monday, same time, same place. And every Wednesday, I don't know if it's the same place, but it's in terms of the same Zoom ID, but it's the same time. Noon at Wednesdays, we have the Cassandra lunch, and Mondays, we have Data Engineers lunch. So thanks everybody for joining. Good show, Nikita. Good work. See you guys soon.